Okay, folks, so we're looking at our first optimization example here, and hopefully you've had a chance to read over these steps here and notice that I follow them as we go through. All right, so what's going on here? Farmer Brown wants to build a pasture with 6 pens as shown below. Suppose he wants a pasture with at least 120,000 square feet. What are the dimensions that will minimize the amount of material used? Okay, so the first thing is, as we talked about in the last section, let's identify the superlative here. This is an optimization question, and we see that we're trying to find the, another way of posing this question is that we want to find the least, there's the superlative, the least amount of material. Okay. And hopefully we see that there's a couple of different potential layouts for this problem. So for example, I could make my pasture look like this. Oops, these need to just have one bar. Come on. So it could look something like this. That would work. That has 6 pens, and maybe you could imagine that having the same area as this. Or maybe you could make a tall, skinny one, something like this. I won't make it to scale, but maybe something that looks like that. Okay. So there's a bunch of different layouts, and they would all have different dimensions in terms of X and Y. And the question is notice they would also use different amounts of fencing. So if all these different layouts, we're asking the question, which of these will use the least amount of material? So running through these steps, the first thing I said is to draw a picture. Well, in this case, a picture was given to us. That won't always be the case, and I highly encourage you to try and draw a picture when it's feasible. Then to determine the optimizing variable, y. Okay? In this case, what we're trying to optimize is the amount of material. Now, I warn you, be very, very careful with these questions. I can ask a Farmer Brown question with a pasture where you're trying to maximize area given a fixed amount of fencing. But in this problem, we're given a fixed area that we have to make, and we're being asked to minimize the amount of material used. So do pay attention. It is always worth being careful in identifying that optimization variable, because two similarly appearing questions might actually have completely different setups depending on what the optimizing variable is. So in this case, we want to optimize material. Okay. So let's see here. Let's go ahead and label another dimension on this. This was called X here. So let's go ahead and call this Y. Okay. And so what is our optimizing function? Well, it would be a function of two variables, X and Y. And here's how I want you to think about it. Let's suppose we created a strand of length X here, and a strand of length X here, and a strand of length X here. Well, that would be 3X, right? We'd have 3 X's. For that strand, and I fix that slightly, okay, and then if you were going to do the same thing for Y, well, we'd have a strand of length Y here, a strand of length Y here, right? You could imagine actually stringing this fence, and so we'd have to make 4 strands of length Y there, so plus 4Y, okay? All right, so here's our function that we want to find the absolute, what? We want to find the absolute minimum of this function right here, okay? Well, what's the problem? Well, the problem is we've got a function of two variables, okay? And we don't know how to find absolute maximum on functions of multiple variables, and that's something you'll learn in multivariate calculus, Calc 3. So our strategy then is going to be to use the constraint to eliminate one of the unknowns in this function. So we need to come up with a constraint equation here. And the constraint equation is what limits you, or it's some extra requirement that you must satisfy in order to satisfy the real-world problem. And here we're told that he wants a pasture with at least 120,000 square feet. Okay. You could make it bigger than 120,000 square feet, but I think we'd agree that if you found a pasture that had more than 120,000 square feet, you could just shrink down the dimensions until you got exactly 120,000. So we're going to shoot for exactly 120,000. So that's the area. So the constraint here is that although there are many pastures that could satisfy this, these particular descriptions of the material used, we have to be considering only the pastures that have an area of 120,000 square feet. So in this case, the area of this pasture must be 120,000. Okay. But how do we compute the area of this pasture? Well, notice that even though we're subdividing it into smaller and smaller pens, notice that the area of this pasture doesn't change. It's still a rectangle, and we still find the area of a rectangle by multiplying the length times the width. So in this case, we get x times y must equal 120,000. So solving this equation for one of the variables, I'm going to go ahead and solve it for x, or excuse me, I'm going to go ahead and solve it for y. We get y is equal to 120,000 all over x. And why did I do this? Well, now I'm able to take this solved constraint equation and input in place of y 120,000 over x into my optimization function. So let's go ahead and write that. Now I'm going to write this as just m of x. Notice that this was m of xy first. Now it's just going to be m of x, and that's equal to 3x. We plug in for, well, here's the 4, and then for y we put 120,000 all over x. Where m of x is equal to 3x plus 480,000 all over x. Now this function now is, as I said, just a variable, just a function of one variable x, and x can take on positive numbers. And that's the real-world domain of this expression. Notice that it's certainly, even if it weren't a real-world story problem, x wouldn't be defined at 0. Okay, so now we can sort of suspend calculus for just a second. We've got just a function, and what are we trying to find? Well, we want to minimize the material used, so we want to find the absolute min of this function. Okay. So to do so, we're going to test the endpoints. We'll notice this doesn't really have any endpoints, and we're going to test the critical numbers. So we need to find the critical numbers of m. So taking the first derivative of m, we get that m prime of x is equal to 3 minus 480,000 all over x squared. If you had trouble with what I just did there, remember that it's helpful to write x as x to the minus 1 power prior to taking its derivative. If you do so, you'll see how I came up with this. Okay. Notice that this expression is undefined at 0. We're not going to call 0 a critical number because 0 wasn't in the domain, or another way to say it, 0 is a boundary point of the domain of the original function. So we don't call 0 a critical number, but we now need to figure out where the derivative is 0. So let's set m prime of x equal to 0, and that happens when 3 minus 480,000 over x squared equals 0, or when 3 is equal to 480,000 over x squared. Here we've got an equation. It's got a fractional term in it. Let's go ahead and multiply both sides by the LCD of the fractions. And so that comes out to be 3x squared equals 480,000. Divide both sides by 3. X squared is equal to 160,000, or x is equal to plus or minus the square root of 160,000, which I believe comes out to be plus or minus 400. Of these, the only one that's in our original domain is the positive term, so our critical number is 400. Okay? At this point, we could use either the first or second derivative test, but I'm here to tell you that for most of these story problems, the second derivative test is going to be easier. Okay? One, it's hard to plug in test points. It's relatively hard to plug in test points into this expression. But it also, this expression kind of cleans up as we take successive derivatives. So it's going to be easier to plug this critical number, 400, into the second derivative. So let's look at m double prime of x. So m prime of x was this expression right here, right? Yep. So if we take the derivative of this, the constant term here vanishes. We would write this as minus 480,000 times x to the minus 2, okay, which would give us 960,000 all over x cubed. And notice that if we plug in this critical number, m double prime of 400, do I care what the actual value is? Do I actually need to plug in 400 cube it divided into 960,000? Well, no, the answer is no. Instead, we just need to look at its sign and notice that this is positive. 400 cubed is a positive quantity, so this is greater than 0. So that tells us M is concave down, where M has a horizontal tangent line. And let me add, it's concave down where x was equal to 400, which is also where M had a horizontal tangent line. So this part's really important, folks. This is where we're utilizing that second derivative test. We said that we have a function that's concave down, and where on this concave down interval do we have a horizontal tangent line? Why, that's right there. And what type of point is that? Well, that's a local minimum. So that tells us, so M has a local minimum at x equals 400. Okay. All right, we're actually going to stop this here. We're going to go ahead and claim that the dimensions need to be 400 is equal to x, and then as you recall, we said that y, what was y here? Going way back to where we solved the constraint for y, we said that y had to be 120,000 divided by 400. So if we solve that for y, it would be 120,000 divided by 400. We get that y has to be 300, so the dimensions will be 400 by 300 at that where we would have a local minimum for our materials used. So that's 400 feet by 300 feet is the, now we've actually only said that it's a local minimum at this point, right? The second derivative test doesn't say anything about where the global minimums are. Okay, so we've actually only said at this point that it's a local minimum for M, but it turns out, and we're going to talk about this in class, that we've actually done enough to say that there is a global minimum at x equals 400. So these are the dimensions. If we make this material, or make this pasture with the dimensions of 400 feet by 300 feet, those are the dimensions that will make this rectangle use the least amount of material, this pasture system. Okay, folks, so now we've worked through that first example. I'm going to let you guys try, I think it's question number 9, or some corresponding question, your pre-work about Farmer Brown's backwards cousin, Farmer Norb. And here's the clever thing that Farmer Norb is going to do. He's going to go ahead and use the banks of the reservoir to form one side of his pasture. Okay, so you need to pick a dimension for this, maybe call this x, maybe call this y. But this is going to be the construct here. So this is the pasture that we're making, and we're using one side. We're assuming that it's a straight, we say that it's a straight bank of the lake. Okay. So in this problem, I want you to be very, very careful here. You're going to follow the work as far as these steps go. These steps that I outlined up here, you're going to draw a picture. I guess I just did that for you. Determine the variable that needs to be optimized. That's the key difference here. In the previous problem, we were asked what dimensions will minimize the amount of material you use. That's what we were trying to minimize. In this problem here, we're being asked to find the dimensions. Again, we're being asked for dimensions, but in this case, we want to have the largest possible area. So in this problem here, your objective function will be an area function. And I'll let you fill in the details there. And your constraint function, or your constraint equation, will be the material used. In this case, he only has 6,000 square feet of fencing. So a lot of the variables are going to be the same, represent the same thing in this problem, but notice that the objective function is now an area function, and the constraint equation is now a materials equation. Give it your best shot, and then we'll take a look at it again tomorrow.